What is actually happening with 3 ʻAumuamua? On July 1st, 2025, a telescope in Chile detected something moving. Not unusual. Telescopes detect moving objects constantly. But within hours, something about this one triggered a different kind of response. Not excitement, caution. By the time astronomers had gathered enough observations to calculate its trajectory, they realized what they were looking at: an object from outside our solar system, the third one ever recorded, and it was already raising questions no one knew how to answer. The object was given a designation, 3I/Atlas. The 3I marks it as the third confirmed interstellar visitor. The Atlas comes from the survey telescope that found it, the Asteroid Terrestrial Impact Last Alert System. Within days, follow-up observations revealed something critical. It had a coma, a faint, fuzzy envelope of gas and dust surrounding a solid nucleus. It was a comet, not an asteroid like ʻOumuamua, the first interstellar object discovered in 2017. Not ambiguous. A comet displaying classic cometary behavior as it approached the sun. This should have been straightforward. Comets are icy bodies. When they get close to a star, the ice sublimates, turns directly from solid to gas, creating tails of dust and charged particles. We've observed thousands of them, but 3I/Atlas wasn't behaving quite like the others. The composition was unusual. Spectroscopic analysis showed it was unusually rich in carbon dioxide, one of the highest concentrations ever measured in a comet. The ratio of carbon dioxide to water was roughly 8:1, far higher than typical solar system comets. It also had high levels of nickel vapor, but almost no iron. In most comets, nickel and iron appear together in roughly equal amounts. In 3I/Atlas, the iron was missing. The coma exhibited extreme negative polarization. The way light scattered off the dust particles was stronger than anything previously recorded for a comet at that distance from the sun. And then there was the tail, or rather, the lack of one, at least initially. When 3I/Atlas first rounded the sun, some observations showed what appeared to be a jet of material pointing toward the sun rather than away from it. An anti-tail. This structure disappeared within days, replaced by a more conventional tail extending tens of thousands of kilometers into space. These weren't violations of physics. Comets can have unusual compositions. Anti-tails have been observed before in solar system comets, caused by viewing geometry and the way dust particles lag behind the comet's motion. But taken together, the features created a profile unlike anything in the existing catalog. The public response was immediate. Social media filled with speculation. Headlines asked whether this could be something artificial, a probe from another civilization. The scientific community responded very differently, not with excitement, but with methodical caution. Because unusual doesn't mean impossible, and it definitely doesn't mean artificial. The history of interstellar objects is short, but instructive. When ʻOumuamua was discovered in 2017, its elongated shape and unexpected acceleration prompted similar speculation. Some suggested it could be a light sail, an artificial structure designed to be pushed by starlight. Most astronomers rejected this. The acceleration was consistent with outgassing, even if no visible coma was detected. The shape was unusual, but not inexplicable. Natural explanations, while incomplete, were still more probable than artificial ones by orders of magnitude. With 3I/Atlas, the pattern repeated. One prominent researcher proposed that the object's characteristics might indicate artificial origin. The trajectory aligned closely with the plane of the solar system's planets, within 5 degrees. The composition was anomalous, the behavior unexpected. But other scientists pushed back, not with dismissal, but with alternative explanations. The trajectory alignment, while unusual, was within the range of statistical probability. Thousands of interstellar objects likely pass through the solar system undetected. Some will have orientations that seem improbable after the fact. The high carbon dioxide content could indicate formation in the outer regions of another star system, where temperatures were low enough for CO2 ice to condense. The missing iron could be explained by observational limitations. Nickel emissions are detectable at greater distances than iron, and the comet was still far from the Sun when these measurements were taken. The antitail had been observed in other comets. The mechanism was understood. None of these explanations were complete. None answered every question, but they were plausible. And in science, plausible natural explanations carry more weight than speculative artificial ones. Not because of bias, but because of base rates. We know comets exist. We've observed thousands. We don't know that interstellar probes exist. We've observed 0. The prior probability matters. So what is 3I/Atlas, if not something engineered? The leading hypothesis is that it's a pristine fragment from another planetary system. Spectroscopic studies comparing its light signature to samples from NASA's Antarctic meteorite collection suggest it may be a carbonaceous object, rich in carbon compounds, similar to some of the most primitive bodies in our own solar system. Objects like this would have formed in the outer regions of a protoplanetary disk, far from the central star, where volatiles like carbon dioxide could condense into ice. The high CO2 content supports this. So does the dusty, reddish appearance, consistent with billions of years of exposure to cosmic radiation during its journey through interstellar space. Age estimates, based on the object's velocity relative to nearby stars, and models of galactic dynamics, suggest it could be between 7 and 14 billion years old, older than our Sun, possibly among the oldest comets ever observed. This would make it a survivor from the early universe, a time capsule, carrying information about conditions in a planetary system that formed when the galaxy itself was younger. But this hypothesis has gaps. If the object is primarily CO2 ice, why is there so little water? Water is one of the most common molecules in the universe. It should be abundant in any comet. One possibility is that the nucleus has a thick, irradiated crust formed over billions of years of exposure to cosmic rays. This crust could trap water inside while allowing more volatile CO2 to escape, skewing the observed ratios. Another possibility is selective sublimation. Different ices sublime at different temperatures. If 3I/Atlas is still far enough from the Sun, only the most volatile compounds, CO2 and carbon monoxide, might be outgassing while water remains frozen. The extreme negative polarization also lacks a complete explanation. It suggests the dust particles in the coma are unusually small and uniform, but why they would be structured this way isn't clear. Then there's the possibility of cryovolcanism, ice volcanoes driven by pressure from trapped volatiles. This could explain sudden changes in brightness and unusual gas emissions. But cryovolcanism in a comet this small, this far from its parent star, would be unexpected. Every hypothesis accounts for some observations while leaving others unexplained. This isn't failure, it's the nature of studying something for the first time. What 3I/Atlas demonstrates more than anything is how little we know about what exists between the stars. For most of human history, interstellar space was treated as empty, a void, nothing but vacuum and scattered hydrogen atoms. But it's not empty, it's filled with objects. Rogue planets ejected from their birth systems, comets flung out by gravitational interactions, asteroids nudged into hyperbolic orbits, fragments from planetary collisions, entire populations of material drifting through the darkness. We didn't know this empirically until 2017, when ʻOumuamua was discovered. Before that, interstellar objects were theoretical. Now we've found 3. And each one has been different. ʻOumuamua, elongated, non-volatile, possibly a fragment of a larger body. 2I/Borisov, a comet, chemically similar to solar system comets, unremarkable except for its origin. 3I/Atlas, also a comet, but with a composition unlike anything in our local inventory. 3 objects, 3 profiles. This suggests diversity. If every interstellar visitor we detect is chemically distinct, it implies that planetary systems throughout the galaxy form under different conditions, different temperatures, different elemental abundances, different orbital architectures. The universe isn't uniform, and 3I/Atlas is showing us that in real time by simply existing. The Vera Rubin Observatory, set to begin operations soon, will detect many more interstellar objects, perhaps dozens per year. Each one will refine our understanding of what's normal, what's rare, and what's genuinely anomalous. But right now, with only 3 data points, we are still guessing. It's easy to dismiss interstellar objects as curiosities. Interesting, yes, but not directly relevant to human concerns. But that misses something important. These objects are messengers. They carry information we can't get any other way. The nearest star system to ours is over 4 light years away. With current technology, it would take tens of thousands of years to send a probe there. We're not visiting other star systems anytime soon. But occasionally, pieces of those systems come to us. 3I/Atlas didn't just pass through. It interacted with our sun, heating up, releasing gases that could be analyzed with spectroscopy. It gave us a sample, indirect but real, of material formed around another star. This is the only way we'll study the composition of exoplanetary systems in our lifetimes. Not by going there, by catching fragments that happen to pass through. And what we learn matters. Understanding how planetary systems form in different environments tells us how common certain configurations are, how often Earth-like conditions arise, how varied chemistry can be in different regions of the galaxy. It informs the search for life, because if we discover that carbon-rich, volatile-laden comets like 3I/Atlas are common, it suggests organic chemistry is widespread. If most interstellar objects turn out to be rocky and dry, it suggests water-rich environments like ours might be rarer than we hoped. Right now, we don't know which is true, but each interstellar visitor helps narrow the possibilities. There's something uncomfortable about 3I/Atlas, not because of what it is, but because of what it reveals about how we think. When something unusual happens, a comet with unexpected chemistry, an object with an improbable trajectory, our instinct is to reach for an explanation that makes it less unusual. This is rational. Most of the time, the simplest explanation is correct. But sometimes, things genuinely are unusual, and we don't yet have the framework to recognize when unusual crosses over into genuinely anomalous. With only 3 interstellar objects ever observed, we don't know what normal looks like for this population. Maybe 3I/Atlas is ordinary for interstellar comets, and our solar system comets are the outliers. Maybe high CO2 ratios are common in objects from metal-poor star systems, and we're just seeing a representative sample from the galaxy's older stellar populations. Or maybe 3I/Atlas is genuinely rare, an outlier even among interstellar objects. We won't know until we've observed hundreds, and in the meantime, we're left with uncertainty. Not the kind that can be resolved with better data tomorrow, the kind that requires decades of patient observation to narrow. This is deeply unsatisfying for a species that prefers answers, but it's the reality of studying phenomena with small sample sizes. You can't distinguish a pattern from noise when you've only seen it 3 times. 3I/Atlas is still out there, moving away from the sun now, its speed decreasing as gravity pulls against its trajectory. By early 2026, it will pass Jupiter, then Saturn, then beyond. Eventually, it will leave the solar system entirely, returning to the interstellar medium it spent millions or billions of years traversing before arriving here. We'll never see it again. But the questions it raised won't leave with it. Because the debate over 3I/Atlas was never really about this one object. It was about how we interpret the unknown, about when to accept the strange as merely unfamiliar, and when to consider that our models might be incomplete. About the balance between skepticism and curiosity. There's a tendency, in science, to favor explanations that fit within existing frameworks. This is good. It prevents premature revolutions based on insufficient evidence. But it also risks dismissing signals that don't fit, not because they're wrong, but because they're inconvenient. 3I/Atlas is probably a comet. A weird one, with chemistry that challenges our assumptions about comet formation, but a comet nonetheless. But probably isn't, certainly. And the gap between those two words is where discovery happens. 50 years ago, we didn't know black holes existed outside of theory. Now we photograph them. 30 years ago, we didn't know planets orbited other stars. Now we've found thousands. 10 years ago, we didn't know interstellar objects passed through the solar system. Now we track them. Each time, the evidence forced us to accept something that seemed unlikely until it became undeniable. So when an object like 3I/Atlas appears, carrying chemistry that doesn't match our catalogs, moving on a path that seems improbable, displaying behavior we haven't fully explained, maybe the right response isn't to explain it away. Maybe it's to sit with the uncertainty, to acknowledge that we don't know. Not yet. And to recognize that not knowing is the beginning of understanding, not the end of it. The universe doesn't owe us comfort. It doesn't arrange itself to match our expectations. It simply is. And sometimes what it sends our way doesn't fit neatly into the categories we've built. That's not a problem to be solved. It's a reminder of how much we still have to learn.